Hey everyone, Ryzen here. Bitcoin's UTXO model is a fundamental concept that differs significantly from the more familiar account-based model used in Ethereum and traditional banking systems. In this video, we'll dive into a practical TypeScript implementation of UTXO management. We'll explore how to fetch UTXOs from the blockchain, calculate balances, and select optimal inputs for new transactions, all essential operations for working with Bitcoin's transaction model. The complete source code for this implementation is available on GitHub. Unlike traditional banking systems where your balance is stored as a single number, Bitcoin doesn't actually store account balances at all. Instead, it maintains a list of unspent transaction outputs, essentially a collection of coins that you own and can spend. Your actual balance is calculated by summing up the values of all your UTXOs. Think of UTXOs like physical cash and change in your wallet. When you pay for a $15 item with a $20 bill, you get $5 back in change. Similarly, when you spend Bitcoin, you must use complete UTXOs, like whole bills, and you get change back in the form of a new UTXO. For example, if you have a single UTXO worth 1 Bitcoin and want to send someone 0.3 Bitcoin, the transaction will create two new UTXOs, one worth 0.3 Bitcoin for the recipient and another worth 0.7 Bitcoin minus fees returned to you as change. Each UTXO contains several important fields: transaction ID, which is the ID of transaction that created this UTXO, VOUT, which is the index of the output in the original transaction, value, which is the amount in satoshis, and status, which indicates whether the transaction is confirmed and its block details. A UTXO can be either confirmed, included in a block, or unconfirmed, waiting in the mempool. Let's put our UTXO management code into practice by examining a real Bitcoin address. The following example demonstrates how to fetch UTXOs from the Blockstream API, filter them to include only confirmed transactions, and calculate the total balance. We'll use the query URL utility to make the API request, our getConfirmed UTXOs function to filter the results, and the getBalance function to sum up the UTXO values. When creating a Bitcoin transaction, we need to carefully select which UTXOs to use as inputs. Each UTXO included in a transaction increases its size in bytes, which directly affects the transaction fee. Miners charge fees based on the transaction size, not its value. For example, if the current fee rate is 50 satoshis per virtual byte and each input adds roughly 68 virtual bytes to the transaction, each additional UTXO would increase the fee by about 3,400 satoshis. This is why it's generally preferable to use fewer UTXOs when possible. Our UTXO selection algorithm first tries to find a single UTXO that can cover the target amount, including fees. If that's not possible, it falls back to selecting multiple UTXOs, starting with the largest ones to minimize the number of inputs needed. For demonstration purposes, we'll use a simplified fixed fee estimate. But in real implementation, you'd want to calculate the fee dynamically based on the current network fee rate and the number of inputs and outputs. Bitcoin amounts are typically stored and calculated in satoshis, where 1 Bitcoin equals 100 million satoshis to avoid floating point precision issues. When working with the Bitcoin network, we convert between these two representations. This conversion ensures precise calculations when working with UTXOs while providing user-friendly BTC values in the interface. Understanding and implementing UTXOs management is crucial for building Bitcoin applications. The TypeScript implementation we've explored demonstrates the core concept of fetching UTXOs, calculating balances, and selecting optimal inputs for transactions. These fundamentals serve as a foundation for building more sophisticated Bitcoin applications. If you enjoyed this content, please like the video and subscribe to the channel.